My name's Sadhu Johnston. I'm Commissioner with the City of Chicago's Department of Environment, and we're on the green roof of City Hall. It's 20,000 square feet of prairie, 12 stories above street level in downtown Chicago.
Green rooftops like this can be as much as 60 degrees cooler than conventional black tar rooftops. These air conditioning intakes for City Hall are located directly over the green roof.
And that makes it easier to air condition inside, which of course air conditioning generates heat. So that's less heat that we generate when we're putting a green roof on, brings our air conditioning costs down and keeps the ambient environment cooler.
The Prairie Garden has saved City Hall $6,000 a year in energy costs, eliminating the need for power plants to produce 45 tons of CO2 emissions. It also helps reduce the amount of stormwater that floods into Chicago's overtaxed sewer system.
This green roof, we've got between 2 to 4 inches of soil, and it's a super light soil. It's 80% inorganic, so it absorbs that rainwater and actually holds it for about a 48-hour period, during which time the plants can use it or it can evaporate, so less of it gets into the storm sewer system.
Most black tar roofs need to be replaced every 20 years. But Chicago City Hall's green roof may not have to be replaced for 50 years or more because the layers of soil and vegetation protect the roof membrane from harmful ultraviolet rays.
There's hundreds of thousands of people that look down on this every day, and people have actually moved their offices to buildings that overlook this green roof because they enjoy the beauty. So it does have a quality of life impact as well as an economic impact.
Though the initial investment is high, a movement is underway in Chicago to encourage the greening of rooftops across the city. The results could ultimately save millions of dollars and play an important role in reducing global warming.
Imagine flying over the city, being a bird and flying over and looking down and seeing prairies instead of black rooftops that are cooling the city and capturing stormwater, really bringing the city to its ecological function, which is a beautiful prairie city.
In this vision of the future, the rooftops may be green, but reducing the carbon footprint of air conditioning systems will still be one of the biggest challenges for the environment.
Most buildings, they actually create more heat within their operations. An office building, for instance, is a heat generator. It's in part the equipment in the buildings, it's the lighting, and actually it's the people. People are a tremendous heat load upon our buildings.
Some of the most cutting-edge research on how to cool buildings is being done here at the Advanced Thermal Conversion Laboratory.
Come on into the lab. We can test any kind of heating, ventilation, or air conditioning equipment that might go into a building. Of course, we're interested in ones that are ultra efficient.
Like something out of a science fiction movie gone mad, all these tubes and conduits can actually finally measure the effectiveness of almost any heating or cooling equipment.
These big ducts are where we put the air in that might have a Miami summer condition or an Alaska winter condition. And this is one of our test objects. This is the air coming out. And we have sensors all through here. You can see we can measure things like temperature and humidity and the exact nature of the air coming out.
The equipment being tested today may look strange, but it's actually part of the next generation of ultra-high efficient air conditioning. It's called a desiccant enhanced evaporative cooler. It's a name only a scientist would like, but it's a technology all of us will love. And as the name implies, it uses desiccant to supercharge an evaporative cooler, unlike traditional air conditioning, which basically uses coolant to blow chilled air into a room. Desiccants are liquid salt solutions, like lithium bromide, that have the ability to absorb water and dry out the air. That produces a low dew point and increases the cooling capacity of an evaporative cooler, producing a more comfortable temperature and humidity level in the home. The wet desiccant then cycles around, and when hot air hits it, it expels the water, which evaporates away into the outside air. It's one of the unique properties of desiccant. The way you dry it out is with heat. In essence, it uses heat to cool.
Fortunately, it takes a very low-grade heat. This is the kind of heat you can get from a solar collector.
The dry desiccant is then cycled back and is ready to be used again and again to pull more water out of the air. When fully operational, the prototype seen here will use 1/4 of the power of a conventional air conditioner, and that means fewer carbon emissions. It could forever alter the way we cool our buildings.
We thought, how could we put all those things together? Me and another researcher put our heads together and we came up with this. And we were like, aha.
It has the potential to really revolutionize cooling technology, just make it much more efficient.